get started with the chain rule. I am starting with the babyest chain rule I can because I want to up this and make it more and more ugly. So according to the chain rule, e to the something. The inside function is 2x. So you get e to the 2x when you differentiate e to something. You get e to the something. Oh, wait a minute. Don't you finish with times the derivative of the something. When you agree, this case, it's just 2. And then you would make it look pretty. There's not an awful lot you can do. You get that. Now I'm going to put in a constant. Whenever you get a letter that's early in the alphabet, like A, B, C, D, the convention is it's treated as a constant. A constant is a fixed number, you just don't know what it is, right? So it's like 5x or 2x. Now, if I did the chain rule on this guy, it would be e to the something times the derivative of that something. What's the derivative of bx?
B.
B. And so you would get b e to the bx. Now I'm going to have a constant a e to the power of bx. Okay, now that's a constant, a fixed unknown number. That's a fixed unknown number. So if you differentiate this using the chain rule, don't you get a e to the something times the derivative of that something? What will the derivative be?
B.
B again. And if you make it look pretty, it now looks like that. Now, well, let's change the letters. Let's do the variable t. The cosine of pi t. Chain rule. It's not the cosine of t. If it was cosine of t, I wouldn't need the chain rule. It's the cosine of pi t. It's like 2t or 20t. So it's a cosine of something. If you differentiate the cosine of the inner function, you get negative sine of that something times the derivative of pi t, which is pi, and then you stick it at the front because it looks nicer there. Now I'm going to put all of that mess together. And we're going to look at how to differentiate a guy that looks like that. 3e to the power of 2t, sine of 2 pi t. Well, the first thing I hope you recognize here is that this is a product rule. Are you comfortable about recognizing that it's two things multiplied together? So I am going to have to do a product rule, f dash to j plus f of g dashed. Whenever things get ugly, I tend to do the working at the side. So f is going to be 3e to the 2t, and g is going to be the sine of 2 pi t. And now I need to know what the derivative is, and then plug all these into here. Okay. 3e to the something gets you 3e to the something times the derivative, which is 2. So that ends up being 6e to the 2t. Are we good with that one? Right. Let's do a derivative of this guy. Sine of something, its derivative is the cosine of that something, times, and what's the derivative? Oops, there's a 2 there. What's the derivative of 2 pi t? What do you get for the derivative of 2 pi t?
The 2 pi.
Yep. And then if you make it pretty, 2 pi cosine of 2 pi t. So now I've got all the pieces. We'll put them in here. The derivative of f is 6e to the 2t times the untouched j. plus the untouched f, which is this guy, times the derivative of g, which is 2 pi cosine of 2 pi t. And to finish with, we need to do style points. Is there any common factors that belong to both these terms? Any common factors you can see?
3e to 2t.
Agreed. Is there any other, it's a number this time, is there any other common factor?
I said 3e to 2t.
Oh, you said 3. Is there a bigger number than 3? Do you notice that guy is being multiplied by this guy? I just haven't bothered to do it. If I did multiply it, wouldn't you get 6 pi out of this? Do you see what the new constant is then? You can get 6. So I'm pulling out a 6. That leaves me with sine 2 pi t plus pi, the cosine of 2 pi t. And if you're kind of wondering what I was talking about here, if you multiply these all together, you get 6 pi e to the 2t cosine of 2 pi t. And this one, I don't really need to do anything because it looks kind of nice. There. Does it make it a little bit more obvious that it's 6 e to the 2t? And, you know, I guess the moral of that story is sometimes you need to do a little bit extra working so that you can make sure you've got the highest. And we are done. And that question is a version of number 10. Actually, it's a version of number 10 and number 11. So I'll try to do as many examples as I can. This is a version of question 8. Now we're going to differentiate this. Forget about this for a minute. Would you agree that the derivative of plus a is 0, so I can forget about it? So all I need to do is focus on this thing. Oh, isn't it another product rule? And I guess I'll do it down here. The f is the square root of r, and the g is e r to the power of 4. So the product rule is going to be f dash j plus f of g dashed. And I'll move it over here because I need more room. I need to differentiate the square root of r. Is there anything I can do to make that easier to figure out? Is there another way to write the square root of r?
Turn it into an exponent, r to the 1/2.
Right. Would you agree that's the only way out this problem? You need to write it like that. Now I'll differentiate, and that's going to be multiplied by the power and reduce the power by 1. And I'm going to make that a little bit prettier, and then make it look like the original. Now if you differentiate, so it's 1 over 2 root of, if you differentiate this guy, it's a chain rule. It's e r to the 4 times the derivative of r to the 4, which is that guy. So I'm going to have f dashed, which is 1 over 2 the square root of r, times the untouched j, plus the untouched first guy, times this fella, e r to the 4 times 4r cubed. We have a style point issue here. I need this guy and this guy together. Well, the answer is going to be 4. But how do I get them to combine into a single power of R?
You add the exponents together.
Okay, so I'll call it R to the half, R3. That gets me, what, 3.5, which we call 7 halves, which I can now convert into that. That is a pretty ugly piece of tidying up, isn't it? I'm looking at those two terms. The only thing I can see is that guy. So I have this fella and that guy. And I would call that one done. We're going to be using, as we have been for the last week or so, a lot of algebra, right? Turning things into fractional pairs, pulling out common factors, you know, doing all those kind of, making it look like the original. That skill set gets better the more you do. Oh, God in hell. I don't want to do that. I have to. I don't think I've done one like this. And I really would prefer not to. But we do know how, or we do need to know how to do it. Wow. Before the chain rule was invented or created, whatever they do with the chain rule, the only way I could do this would be defoiling this out. Can you imagine how ugly that would be if you multiplied it times the other one? You trust me, you would have a thing that would be like 5 lines long, hugely ugly polynomial, and then you do the power rule, and the answer would be equally ugly looking when you're finished. Instead, I'm going to recognize this as 2 things being multiplied. And I'm going to do the trick that I tend to do, and that is essentially do the building blocks over here. So I know what the derivative is going to be. Since it's a product rule, it's f dash g plus f of g dashed. But all the pieces I need, I'm going to do over here separately. So there is f. This is a chain rule, right? Something cubed. So 3 times something to the power of 2. Finish with the derivative of the inside function. So if you differentiate 4x add 6, you get 4, and a little bit of tidying up, I end up with 12 of these guys. Okay, now look at G. G is this guy cubed. And that's also going to be a chain rule, because that's essentially something cubed. So you get 3 somethings squared. And you finish with the derivative of the inside function, in this case, 2x take away 5. If I rearrange it just to make it a little bit prettier, are you comfortable with that? The f and the g and their derivatives. Time to put that information right in here. So what do we have? We have f dashed, which is this piece, times the untouched g, plus the untouched f, times g dashed, which is, I don't have room, so I'll write it underneath. 2x take away 5, x squared take away 5x add 6. This term, this term. Let's look for common factors. What's the largest power of 4x plus 6 that I can suck out of both these expressions? What's the largest power of 4x plus 6 that I can suck out of this?
Two.
2. What is the largest power of this quadratic that I can suck out of each of these? And I just realized something. There we go. What's the largest power of the quadratic that I can suck out of both of these?
Also 2.
Also 2. And hopefully I've got enough room to put in what's, oh, hold the horses. There's a 12 here and there's a 3 here. So doesn't that mean I can pull out a 3 as well? Okay, now I can do it. 3 into 12 gives me 4. All used up, one of these left. Plus one of these left, one of these never used and used up and used up. So plus a 4x add 6 with a 2x take away 5. So we're looking at 3 lots of this guy squared times this guy squared. And what do you think I'm going to do with all of this stuff that's left over? This guy plus this guy. What do you think I should do next?
Oil it out and combine like terms.
Yes. Can you just trust me, because I've got the answer over here and I don't want to go through it all, that it ends up being that. You can check it out, but they tell me it's equal to that. So I'm going to assume that it is. Unless I misread the question. No, I don't think I did. That can't be factored, so it's finished. You know, some quadratics can be factored. If it could be, you need to factor it as well. So what you're doing here, you're doing common factors, you're doing foils, you're doing collecting like terms, you've got a quadratic at the end, that quadratic might factor, in which case you turn back to 2. Can you see all the different versions of algebra that could be in just one question? You know, multiplying, collecting terms, factoring, and all that good stuff. Okay. This one is a version 14. It's not that bad, but I'll do it. In fact, I might have done it before. It's a pretty straightforward one. This one isn't anything as bad as that one. Would you agree this is just an e to the something? So if you differentiate e to the something, you get e to the something. And the derivative of the inside function, hopefully we're getting faster at this. What's the derivative of tan theta? Derivative of tan theta.
Secant squared.
That's the one. Now with the midterm coming up, you really need to try and memorize as many things as you can, because if you have to keep looking for bits of paper where you wrote down things like derivative of this and what that is equal to and what this formula is and so on, you break up your thought process. First, it'll take you a lot longer to do, right? Because you have to go and find things and make sure that the thing you found is the thing you were looking for, right? And that breaks up just the thought process. See, because we know this one, isn't that very quick question? If you didn't know this one, you have to go and look, and then, you know, time, you end up half your time looking at stuff, right? So I'm kind of reaching a natural changeover point. We're still on the chain rule, but we're now going to look at chain rule on steroids. Chain rules where some really, really ugly things are going to happen. And that means that you're going to have your thinking cap on and stick with it. So here's right out the bat an example of a ridiculously ugly chain rule question. We've done a few chain rule questions that had another process. Haven't we done a couple of product rule questions that had some chain rule stuff in them, right? We've done that. This is an example of a chain rule and a quotient rule. Now, when I look at this question, the way I see it is something to the power of 10, right? And that something is downright ugly, right? It's that fraction. Isn't it still a chain rule, something to the power of 10? So to get the derivative of this guy, it's 10 somethings to the power of 9 times, and I'm going to do this, I haven't needed to do this before, times the derivative of the inside function. Does that make sense? That the derivative would be 10 of these guys to the power of 9 times the derivative of this guy. Now, when you look at this fella, it's probably a good idea to do him separately over here. So suppose I wanted to find the derivative of this guy. What method would I use to find the derivative of this fraction?
Quotient rule.
All right. So can you see why this is a chain rule? We've done the chain rule bit with a quotient rule in it. So in the quotient rule, you call the top f and the bottom guy g. And so the derivative would be f dash g, take away f of g dashed over g squared. Differentiate the top, you get 3u squared, leave the bottom alone. Take away, leave the top alone, and differentiate by the bottom. And then all over whatever the bottom has, squared. Now, the next thing I'm going to do is distribute, take all of this, subtract all of that. So let's see if I can get it right. That times that is 3u to the 5. That times that is plus 9u squared. Right, make sure I take away things. This guy times this guy is u to the 5, but I take it away. 3u to the 5, I should say. This guy times this guy is negative 9u squared. But when you subtract the negative, you end up adding it. And so it looks like that. And this guy gets killed off by this guy. And these two combine. And so I now have 18 of these guys all over that. So I can now return to my original, this one, and write down 10 of these guys to the power of 9 times the derivative, which I've now found. And there's a little bit of tidying up we can do, but there's actually a lot of tidying up we can do. I want to make this as pretty as possible. So I'm going to go 10 times 18 times u, and I'm going to get 180 u squareds. I have got this ugly fraction to the power of 9, but I also have a couple of squares here. And I would like to take this and somehow make them combine. So I'm going to take this and split it. And that's an algebra trick you're allowed to do. And now I can have this piece, and this can join with this. And so what I end up with is 180 u squared, u cubed take away 3 to the 9, all over, these get added together, and you get a u cubed add 3 to the 11. You see that's a little bit prettier looking than the original. That is one ugly question, isn't it? That is a messy question. But quite an elegant answer. Now, I told you we're in the horrible world, so here's another one. I'm going to do a square root of 1 plus cosine t over 1 plus sine t. And the whole thing is in a square root. And this one is going to be a chain rule and a quotient rule as well. If you see a fraction, you're going to do a quotient rule, right? There's no way around it. And if you see an ugly thing inside a square root or a cube root or to the power of 10, you know you're going to do a chain rule. First thing I'm going to do is rewrite this as a half power. Chain rule coming up. Something to power a half. Multiply by the power and reduce the power by 1. Then you find the derivative of the inside function. Now that guy, I'll do separately. It's a quotient. Top is f, bottom is g. We're going to be doing f dash g, take away f g dashed over g squared. Differentiate 1 plus cosine, all you get is negative sine t. Leave the bottom alone. Take away, leave the top alone. And differentiate by g, gets me that. And the bottom looks like that. Now distribute, you get negative sine t, take away sine squared t, take away a cosine t, take away a cosine squared t, and you get a 1 plus sine t squared. Negative sine squared t, negative cos squared t. It's an identity. If it was positive sine squared plus a cos squared, wouldn't it be 1? Right? It's negative sine squared, negative cos squared. What do you think that's equal to? Right. Sine squared plus cos squared is 1. Negative sine squared, negative cos squared is?
-1.
It says -1. If you've never seen it before, now you have. So I'm taking this answer and plugging in here. And hopefully we're finished, but I know we're not. It's a half. A really ugly looking negative half power, followed by a negative sine t and negative cosine t take away 1 over a 1 plus sine t squared. Can't really do much with the half, can't really do much with that guy. This fella here is a problem. In fact, he's such an ugly problem, I'm going to do it separately. I want to find a nicer way to write that. Okay, any suggestions about what we could do with a negative half power? Algebra, what can you do with a negative a half power?
You just flip the denominator and numerator and make it square root.
Oh, that's interesting. If I picked you up correctly, are you saying that you could flip these two things around and make it a half?
Yeah.
And then, well, you nailed it. That's not the way I was going to show it, actually. But I like that way because it's actually quicker. Or you could have written it as this fella. And then you separate it out as this fella. One of them's a sign, or that bottom one's a sign. So let's focus on this guy because I like him. I'm now going to call it that guy to the half over this guy to the half. And then I'll put the square roots that you wanted in. I kind of like that version better. So I'll now zoom over here. What do we have? Well, we have we have a square root of 1 plus sine t. We have the square root of 1 plus cosine t. We have an ugly expression that looks like that. And we have a 1 plus sine t squared. This 1 plus sine t squared and this half power, which is what a square root is, they can interact, can't they? They can cancel. If you have a half power on the top and a square on the bottom, when you cancel them, don't you get 3 halves left and it's on the bottom? So that means that I now have, and there's the 2 there, I now have negative sine t, negative cosine t, take away 1. And on the bottom, I have 2 lots of this square root and 3 halves gets me that guy. And I can guarantee I could give that same question to my Calc 4 students and I'd be lucky if a quarter of them got it right. So if you could follow that one, your algebra skills are at least in par with those students. Is that going to be a midterm exam question? Probably not. I think it's a bit unfair. He would give you like the worst case scenario, which is what this is. You typically get the middle of the road questions, some a couple easy, some a couple of bits harder, but mostly middle of the road. But it is a question that you should be able to do. So we are still working on the last phase, which is the ugliest versions of the chain rule. That's chain rules that involve product or quotient rule. And then I'll show you a chain rule that involves a chain rule. So, something to the ugly power, according to the chain rule, is e to the something times the derivative of the something, right? This one's not anywhere near as bad as that one. So e to the something, its derivative, e to the something times the derivative of that inside function, the something. Excuse me. That means I need to find the derivative of this fraction. As I said, it's not the worst looking one in the world. You agree it's a pretty simple quotient rule. So I'll call this F. I'll call this J. And now I'm just writing down the quotient rule. So differentiate that guy, you get 1. Leave the G alone. Leave that alone and differentiate that, you get a 1. And on the bottom, you get that guy squared. If you distribute this, and then you subtract the Z, it becomes actually a very nice answer. Looks like that. So it's going to be e to the ugly guy times -3 over z minus 3 squared. You really can't make this pretty, except maybe in the order that you write them. So thankfully that question's finished. Right. Now compared to the last one, isn't that a lot cleaner? Right, so could I give you that one in the midterm? Yes, I think that I would consider that a difficult one, but not impossible. Right, so it is, you could get one. Not saying you will, you could. $18. Here is a question that has a chain rule, a product rule, and another baby chain rule inside it. If you want to differentiate e to ugly guy, you get e to the ugly guy times the derivative of that ugly guy. It's quite familiar, we've done that a few times. And when it gets difficult, I do them separately. Would you agree this is a product rule? Call this F, and I'll call this J. So the derivative of it is going to be F dash G, F of G dashed. Differentiate this guy, you get 4. Leave that one alone. Leave this guy alone, it's 4t. Oh, if you differentiate the sine of 2t, isn't that actually a little baby chain rule? Isn't it the sine of something? Right, the sine of 2t is a chain rule. If you differentiate the sine of something, you get the cosine of something times the derivative of that. Do you see where the extra times 2 comes from? From the derivative of the 2t that was hidden inside the sine. So technically, isn't this a chain rule, a big ugly chain rule, and then later on a little baby chain rule? Now, if you make that look pretty, you get 4 of these guys, and you get 8t of these guys. So I should basically be pretty much finished. It's going to be e to that guy times the derivative. And that's 4 of these fellas plus 8t of this fella. Is there anything I could do to this, even if it's just a minor alteration, to make it nicer in style point rules? Is there anything you can see to do in this expression?
Could you factor out the 4?
Yeah, it's not much, agreed. To be honest, if that was a test question and you didn't do that, I probably wouldn't take any points off. Would you agree it's almost like cosmetic? Do you think it's not really helping much, right? Some common factors make a lot of difference, right? It makes the answer look much tidier. But in this case, it doesn't. But if we're sticking to the lawyer rules, it should be done. And then we are good. Right, finished. Yeah. There are a couple of more questions to go on this list. There is a horrible question 19, but I've done one like it. I can find it now. Question 19 is just like question 15. So if you look back at how we did that one, that'll get you through 19. I'm just talking through the last few. If I gave you a question like this fella, would you agree that's just a product rule? And wouldn't you have to do a chain rule on the 4 minus x squared piece? If I gave you, that 21 is pretty obvious, and 22 maybe, you need a little help. If you were being asked to differentiate this guy, wouldn't this be a chain rule? So the derivative would be something cubed, so 3 something squared. But then you'd have to find the derivative of 4 plus cos squared z. Isn't cos squared z, cosine z in big brackets all being squared? So isn't that actually another chain rule? Next one, pretty straightforward, and we're done. So I'm going to give you an example of a question that Elizabeth O'Neill likes to give her students when she does chain rules. Here is a weird function, e to the power of e to the power of e to the x. Put your last name down for attendance, and then we'll see if anybody here can do that one as our last chain rule question. So once you've got your name down, have a look at it, see if you can figure out what on earth the chain rule for that one would get you. Because technically, I call these Russian doll questions. Aren't these chain rules inside chain rules inside chain rules? Like those little Russian dolls that are inside each other. Okay. E to the ugly guy. So its derivative is e to the ugly guy times the derivative of the ugly guy. If you want to differentiate this fella, it's e to the ugly guy times the derivative of the ugly guy. So you get e to the x times e to the x times e to the x. There's something elegant about that, isn't it? It's got a little triangular kind of shape to it.